I have now record.
Yeah, thank you.
Oh, it's a recording, right? Okay. Yeah. Yeah, thanks for the reminders. That's important. So you have a black and then white and then the gray color, 3 color. So the idea is that initially all the graph is white. Then this is white, and you select the first node, which is source. Source is black. So you start with the source. Then the adjacent node of a source become gray. Or the adjacent one around is called gray. Then outside is white. So it's a very important 3 type of nodes. Start with one black node. Outside is a gray. Then all the other nodes is white. So Dijkstra algorithm is simple, is that each step you select a gray node. And gray node, you just want to find out the distance from the black node, which is only 1, right? This gray node, gray node. You pick a one with the smallest distance. Can you see it? I hope you can see it, right? You select the one, yeah. Select the one with the smallest distance. Then once you select, then that gray node becomes a black node. So you change the structure. So that means you include the one gray node to the black node set, then it becomes bigger. Right? So in general, you can see that inside there are lots of nodes already selected black. Then the adjacent node towards this black node is called the gray node. So this is like adjacent node. Then among all the adjacent nodes, you find a node with the shortest distance to this root, which is a source. So each time you find a node, so this area will become like a tree, right? Spanning tree. Then you find one of the gray node with the shortest distance, you include it. You further expand. As you expand this black node territory, then the gray node also change. Then the white nodes outside, further outside, become smaller and smaller. When all the nodes become black, then the algorithm stop. Okay, so this is the shortest path algorithm. So the great thing about this Dijkstra algorithm is greedy and also it solves a more general problem. General problem means they find the shortest path to all the nodes, not just one node. Right? Although technically, sometimes you don't have to explore to all the nodes, because why? Because once you find a destination node, this is destination, you should stop, right? So suppose this destination is included in the black node set, then you stop. And so this is the basic idea. It's very powerful, and this is a problem which is a difficult problem, but using a simple solution to solve, and the proof technique also very simple. Any question on that? No questions. Then last time we also discussed several extensions. Right. So remember this black and white and gray nodes, right? So one extension is that you can start the algorithm both ends. So you expand and you expand, right? So this is a black node set for the S, black node set for the destination source. So inside there's like a spanning tree. Okay. Whatever spanning tree, there's inside spanning tree. And outside there are lots of gray node, right? Sooner or later, these two connect, right? These two connects. These two connects means that these ones connect to one another. Once they connect, the algorithm stop. Okay. And although in terms of asymptotic complexity, it's the same. But usually if you run this one, this is much faster. Why is that? You can use a simple explanation. Just imagine that the distance between S and D, right? Whatever the distance. So if you do it suppose this distance, S to D, just hypothetical is L. So when you expand this territory, probably each side will get half of L, like a radius, although we haven't defined the radius. It's just kind of radius, right? So each side get half of the radius, then they will meet. So you can see that the total size of these circles, so it's just two small circles. But if you do the traditional Dijkstra algorithm, right? Traditional Dijkstra algorithm, so what's the idea? It's the same, S and D. But this is only from one side. So that means you have to create a radius of what? L to reach D, right? So you can see that in terms of area size, this is much bigger. So you can get an idea why this is the other one is faster. Okay, so this is the one extension. Another extension, or this type of greedy algorithm, is used for minimum spanning tree. Minimum spanning tree is very useful. What's minimum spanning tree is how you connect, just imagine each node or node is just like a house, using minimum number of cable, right, to save money. So this is a minimum spanning tree. In fact, there's an algorithm called Prince algorithm. We all know Prince algorithm. Using the same idea of Dijkstra, although they probably presented a slightly different way. So the same idea, you have a black node in middle or in center. So that means this is the set of sub-node spanning tree already constructed. Then outside all the gray nodes, right? Gray nodes mean connected to one of the nodes inside, or multiple nodes, doesn't matter. So those are the gray node. Further outside is the white node. So the idea is the same. Each round you pick a one gray node, put in the black node set, and this black node set territory keep on increasing one at a time. But the difference of selection criteria is different. What's the selection criteria? You just look at one edge. There's a weight, means a distance, from this gray node to one of the black node. You pick the one with the minimum weight. Minimum weight is the edge weight. So what's the difference than this one than the Dijkstra algorithm? Dijkstra algorithm is there's a source, right? So it's the shortest distance from source to one of the gray node. So it's from one particular nodes to the white node. This minimum spanning tree is different. You just pick an edge connecting a black node and gray node. That edge is the smallest minimum weight. So using the same idea of greedy, you can prove that this will construct a minimum spanning tree. But if you look carefully, these two algorithms very similar idea. Just measuring the selection criteria is different. Right? So this is kind of interesting things we need to learn. Right? So this is one greedy one. Now let's go back to the slides. Let me see if I hope you can still see the slides. Can you see the slides?
No.
Oh, it's not the share. So it's a share. So you can see, right?
Yeah.
Yeah, the slides. So last time we also discussed another interesting algorithm, which is useful. If you recall this one, the greedy one is a coin changing. So coin changing is that in US, just this example, a common used denomination for coin is $1, 25 cents, 10 cents, 5 cents, and 1 cent. Right? So there's a good strategy for you to make changes if you go to a grocery store, a greedy approach. And the result is using minimum number of coins. And it's very easy to calculate. All you need to do just do the addition. So what you need to do is that in this example, $2.89, you pick the maximum key thing, maximum denomination, smaller than the changes. So in this case, $1. So you can add $1, right? So you subtract this $1, or sometimes people do it addition. So like a two-part. So you have this side is a 2.89. This side is $1, right? So you can keep adding another one. What's the maximum denomination you can add to the $1? But total amount still should be less than $2.89. Well, that's simple. It's another dollar. Then they get a $2, right? Then can you try the one more dollar? No, because if you add one more dollar, it becomes $3. It's more than $2.89. This is what cashier calculate, right? They don't need actually any like a calculator. Just keep on adding. So you know that $2, then the next one should be you try as a quarter. Then it's $2.25, still not reaching $2.89. Then you add another quarter, then $2.50, then another quarter, $2.75, still less than the $2.89. It's fine, but you cannot add one more quarter because otherwise it would be $3. So you add dime, so it becomes $1.85, right? Then you see that 285. You cannot add any nickel, because if you add nickel, then it's already exceed. It's 290. So you can only add a penny. You add a penny, 186, add one more, 87, then 188. Oh, sorry, 288 and 289. Right? So this is how they do the greedy algorithm. So why this is such a magic? This greedy algorithm always optimal? This depends on the denomination. It's a very important denomination. If a country they design a denomination in a different way, not careful, then this greedy approach doesn't work. So let's look at some example. I don't know whether I need to stop sharing, maybe better, right? To show on the board. So I show on the board, right? This is the board. Hope you can see it clearly. So board is still much better. Let's just give an example. Suppose a country, they have a denomination of 5, 4, and 1. Whatever country, 5, 4, 1. And this is not a good design. Why is that? Suppose you want to make a change of 8, right? 8. Using the greedy algorithm, you will add a 5. The next 4 you cannot do it. It's a plus 1, plus 1, plus 1. Is that correct? So it's a total 8. But this is not the minimum number of coins. In fact, the minimum number of coins for this one is 4 plus 4 equals 8. The main reason is that this 4 is not good. So now you can think about, suppose you're asked to design a new currency system with a different denomination. So how would you design it, right? So there are basically 2 questions. First question is that you design this denomination such that when you use a greedy approach, it guarantees that the number of coins returned is a minimum. Another one is that we give an example last time, like you have a different type of changes. Imagine from $1, I give you $1, you have a change of 1 cent, 2 cents, 3 cents, all the way to 99 cents. Then for each cent, right, then you try the minimum number of coins for return changes. And then you calculate the average number of coins should be minimized. Then obviously it depends on the number of denominations. So if I give you, say that I give you 7 denomination in $1, which 7 denomination is good, satisfy these 2 conditions, right? So obviously US system work means that $1, forget about $1 because we're talking about $1. Suppose you have a 50 cents, 24 cents, 10 cents, 5 cents, and 1 cent. So that means US system right now use 5 denominations, right, to make changes. But in this case, you may have to use lots of coins. For example, 99, you have to change it to 50, 25, 10, 10. So this will give you 1, 1, 1, 1. Is it correct? Yeah, so this is a 1, 2, 3, 4, 5, 6, 7, 8, right? So in the worst case is 8. So can you do something different? So it's up to you, right? You can design. Now, so the question is that if I give you 5 denomination, is this the best one? And you calculate for each one, you calculate the average length. Right? And if I change, say that now I change my mind, I give you 6 denominations. So what's the good way, right? So suppose for 6, you use 50, 20, 10, 5, 2, 1.
Professor, we can't see the bottom of the board. Oh, there we go. Thank you.
Can you see it? No?
Yeah, now it's better.
Yeah. So you can see that. That's quite nice, right? Pay attention to this one. I call this modular design. Really means that if you go to the like less than 10, so it's 1 to 5. Then from 10 to 90, so you have a 10, 20, 50, right? So it's kind of regular. But let's just, for the sake of practice, let's see 99. Hope you can see it. 99. Can you see it? Oh, 99, yeah. So can we use a greedy? Yes, you can do greedy. So we have a $50, 50 cents. Then obviously next is 25 or 20, and 20 is already 90. Then add 5, add 2, and 2. Oh, that's great. We only need a 6. We only need a 6. Now the question, is this the maximum number worst case? In fact, that's the worst case. I'm pretty sure it's the worst case. You can try any number. It will be no more than 6 coin return. Let's just do a practice. Right? So can we do one more practice? Just pick any number. So any student want to give me a number? Then we try. Within $1, the change. Give me any number. No one want to say anything? Don't be shy, just say. Pick a number. Then I will make changes and see how many coins we needed. No one want to try? Then I'll try 88. Okay, how about 88? 88 is 50, 20, 10. Is it correct? Can you see? Yeah. So 50, 20, 10, 5, 2, 1. It's perfect. So you can see that that's the minimum. Not minimum means that 6 is the worst scenario. I mean, compare with this one, the US system, right now you may use up to 8. Obviously, you introduce one more denomination, right? So you can ask this kind of question. So if I give you a fixed number of denomination, what should be the best denomination to satisfy 2 conditions? One is that using greedy algorithm, it works optimal. And you want to minimize the average number of coin changes into when you return. Right. Any question on that? No question? Okay. Now let's do something which is more interesting. Although it's not in the book, I think it's very important. This is what I call the generation. in fact, you see this quite often. Generation means how you enumerate, or it's sometimes called enumeration. Can you see it? Right, generation. So let's just give an example. For example, in a country that kind of weird denomination, very weird denomination. For example, like this, right? This weird denomination. Oh, we can have another one. Just say 55, something like that. All right, these are the coins available. Then they will ask you to say that I want to make a change of whatever, 99 cents. So how you, now the question is that, can you generate all the possible changes, different patterns? Not asking you the minimum, ask you all kinds of things. Probably you're familiar with this, how you do this kind of generation. So one easy way is introduce a stack, right? A stack. Stack means that you push things in, you pop up things. So this actually tells you how you do the generation. And this denomination has order. It's very important, the order. This means of a large to small. You still try it every time you do a change, you push the largest possible. So in this case, you push the 55. Or you can have a ranking, right? 1, 2, 3, 4, whatever. So you can opposite. Rank 5, rank 4, rank 3, rank 2, rank 1. This is 1, right? So you know, you don't have to put this 54. You can just say the R5. You push that R5, you know it's a 54 putting there. Then next time you push another one in. Push another one in this case, they push R4. No, you push R5, right? R5. But R5 is too large, so you cannot do it. So you try R4. Right? So you just keep on pushing more and more, right? Until what? Until you find the solution. Or you find the solution until somewhere it says that you add up, oh, it's 99 cents, you're done. Now the question is that how you systematically generate the next one. Right? So it depends on where you are. Suppose this is R3, the last one. You already added to 99. So the key thing is this one, is that when you do the next one, you should try, you replace R3 by R2 in that order. R2. Okay, then you keep on pushing more and more. Okay, so that's the idea. Until you run out of, like R1, you try all the R1, it doesn't work. So that means your current selection is not good enough. Then you need some kind of backtrack. Backtrack, sorry. Backtrack, right? Backtrack already means that this is already reached the end. So you pop up, so you remove, then go to the next stage. Since this next stage you already try R3, so what should be the next one? Next one should be the index by 1, less 1, right? Then try R2. Then you repeat the same process. So you can see that the whole selection process is push something. When you reach the end, you pop up. But when you pop up, then the next one you should subtract by 1 in terms of index until you reach all the way to 1, right? Then you reach the end. So this is like a backtrack all the way to here. Suppose you imagine this backtrack to here, 5. So that means you already exhaust all the combination with 1, 5, and whatever the other one. So this one already exhausted, then what you should do? Replace R5 by R4, right? They continue the same process. then you just keep on pushing them, pop, pushing, pop. So that's the simple idea. So I'm sure you learned this in the data structure, but I just tell you the importance of sometimes the generation. It is useful in using the stack, right? So some kind of like a keep track of different combination. So it's just like so-called generation means that you generate all the possible sequence to make it the 99. But you have to try different options, but you have to do it in a systematic way. Any question on that? I assume you know all these things, right? But just some refresh your memory. But then some students will say, oh, that's piece of cake. Everyone knows that. So let me just give you some more interesting example. And later you see that sometimes the generation is not that trivial. One trivial example is that you probably know all this. And you go to a park, like amusement park. You have some kind of maze or whatever. I'm not doing good, but. So this is exit. This is the entrance. Okay. Now your job is to find out a way to maneuver, and but the problem is that you don't really know, right? You go this, go this, go this. Eventually, you want to exit. You see that? Now the question is that suppose you are very smart, although you don't really know the direction, but somehow you can record whatever. We can put some mark, right? Some mark. Now, how can you systematically go through all this possible direction, right? All the options, exhaust all the options, because you don't want to repeat the same route, right? Repeat the same route. So how can you do that? The key thing is that is this idea, which is not too difficult, is that whenever you have a crossroad means that whenever you have a multiple option, crossroad. For example, in here, just hypothetical. You can either go this way or go this way. Right? So let's make it simple. Suppose the crossroad is like this: east, north, west, south. Okay. You have this label, or you just remember this one, or you can write a piece of paper. Right? So what you try to do is that you have to systematically try it based on certain order. For example, you first try east. If it doesn't work, try north, then try south or west, then you try the south. Okay. So all you need to do, but this is not sufficient, but you need to keep a piece of paper. Keep it all in your mind. You're very smart. You remember all this thing. Is that you record like a tape. Right? And this is the first crossroad, second crossroad, third crossroad. You see that? Then you put north, south, west, east, and so on. Right? So that means suppose you are at the ninth crossroad. That's the most recent one. Right? Then if you fail, like get it to the dead end. So you remember if this is east, suppose you say the east, north, west, and south. Then naturally what you do is that you try north.
Professor, could you just lower the camera a bit?
Yeah.
Oh, thank you.
So you get that one? Is that whenever you have a cross, you put a piece of paper, you add that what selection I did. You systematically select east, right? First, if you east fail, like a dead end, they come back to the crossroad, right? Next time you should just what? Try north. So you remember north. So when you go to the north, you may go through a few more stop. Then you have a more here, right? Maybe this one, you find out this one all failed, then you come back to north, the same location, then you say next time should be west. But during the exploration, you may find more a crossroad. But what you need to do is just have a very small memory. So it's basically a stack, right? Stack. It's a thing like a stack. So it's always have one entrance, push and pop. Push means that they add one more crossroad. Pop up means that this is dead end. I need to try it, another option. So this is very important data structure, and this helps you to generate all the possible solution. Okay, any question on that? By the way, this approach is discussed, right, in the program technique? Yes or no? No one answer?
I don't think so.
I remember discussing this last semester.
Okay, great. That's good. But one student said no. Who is that? It's okay. You can say it.
I don't recall that we covered that. We did cover stack, but we didn't cover stack for like backtracking purposes.
Yeah, but now you understand?
Yeah.
You understand. So actually it's very powerful, right? So it's very powerful. You just need to remember this crossroad. And then you only need one very simple structure can remember. And then you can do all this trick. So it's a kind of generation. Right? All right, now let's give you a more exciting problem. Also called generation, but this is a much harder problem. All right, so this is actually a problem I gave it 20 years ago to this algorithm class. By that time, we worked in Florida. Okay, so this is the one. So this looks like what? A table with seats, right? And I don't know what's the number, or maybe this is perfect, 2 times 5. So suppose you have a 5 couple, wife and husband. Right? So husband H, wife is W. So you can have H1, W1 means a husband and wife. Right? So there is some requirement because of tradition or custom. Wife can only sit with same gender, means a woman sit together, boys sit together. Or you can sit, the man and woman can sit together if they're a couple. So let me just give you an example. For example, H1, W1, W2, or just have a W3, then H3, then H2, or something like that. Do you see that? You can see, right? So that means woman sit next to the woman, it's fine. But if it's a man, there's a couple. So 1, 1, this is the same, right? So woman, but this is a man, but index is the same, right? So index is the same. Is it clear? So looks like there are many different options. You can have another extreme case is that half of the table, one side is all women, the other side is men, and the 2 adjacent the areas are just couple. Right? Or you can have a interleaved one. Like this case, you have a husband. You can start actually more wife here. I don't know if it's exhausted or not. Probably not, because you can have a husband 4, then wife 4 here. Does not appear, right? So you just can continue. You get that question? So now the problem. Problem means that how you generate all the possible legitimate seating. So this is a typical generation problem. Now even more difficult one, that's a much harder problem, is that how many such number can you mathematically express number of the possible seating? Right? But obviously, you see that if seating get rotation, you see that if a pattern is isomorphic, if you don't remember the meaning of isomorphic, just forget. you can just imagine that this circle becomes a line, like in the theater. Let's make it easy. Right? Since it is connected, but isomorphic one is considered the same, means that you rotate, then it's the same. Now, how many different seating you may have? Now, how you write a program? How you write a program to generate all of them? And what's the fastest program? Actually, if you look at any textbook, you learn data structure, algorithm, no one studied these things. Right? Now, what's the fastest way to run this, to generate all this seating? So this is one of the just some interesting problem for you to think. So probably I don't want to go through more because this is beyond the scope, at least for this class. But you'll remember, this is one set of problem called generation problem. Since we talk about the coin changes problem means that you find a particular solution, which is the optimal solution. It turns out that the denomination is very specific. You can just using greedy get the one optimal solution. But if I change a problem and say that I want you to generate all the possible solution, then you need some kind of generation method to go through all this. Right. Okay, so I thought that this is interesting, we can discuss. Now let's go back to sharing mode. And we can continue. So I think that's it for the.
Professor, I had a doubt here.
Yeah. What's the question?
Yeah, so you didn't explain how did we get the denomination 1, 5, 10, 20 to make 6 coins?
No, we did not discuss that.
Okay.
Yeah. So it's up to you to think about it.
Right? Okay. Yeah.
No, actually, there are many solutions. Just think about this. So there's many other solutions. But the one, you have to have a one, right? I think last time we explained, if without one, you cannot make a change for odd number, not odd number, means just for $1 or 1 cent. So one is essential. But there are many other ways to make it when you try to greedy and it work. I'm pretty sure, for example, you tried instead of 5, you replace it by 6. Say 6, 2, 1. And it still work. Or you can try anything to the power of 2, for example. May work also. You say that from 1, 2, 4, 8, and then 16, 32. Right. Did I answer your question? At least partially.
Yes.
Yeah. So the answer is that there are many solutions, not just one. I already give you the example, right? The example, I said the US system using 5 denomination in $1 or 6, whatever. So it's a 50 cent, or really use quarter, nickel, dime, and then 1 cent. So this is clearly optimal. Clear optimal means that the greedy is always guaranteed. There's another system, which is a Chinese system, is using 1 cent, 2 cents, 5 cents, 10 cents, 20 cents, 50 cents. That's also minimal. Okay. So that's, there are many solutions.
Right.
Oh, you can try, you can develop your, I don't know, are you from India?
Yes, Professor.
Yeah, I forgot, I don't know what's Indian one. It depends on whether you have inflation. If a country with inflation, you don't have a penny or something, you may have like a $10 start. But again, you can try. I'm pretty sure, although I cannot guarantee, almost all countries, their denomination meet that condition, means that if you try the greedy coin change, it will be optimal. It's really interesting, right? Okay, so that's the end. Now let's do a new chapter.
Professor, can I just ask quickly regarding the generating all possible changes? So all possible ways that we can exchange certain denomination.
Yeah.
So could we do it also in reverse? Could we start with all ones, so all 1 cent, and then change, like do it backwards, since we started stack like our R5, R4, R3.
Yeah.
So could we start with R1 and then exchange,
Increase.
for example, exchange, for example, 1 cent to 5 cents and do it backwards.
Yeah. Okay, so let me give a challenge to other students. So let me just give you an answer. The answer is correct. This is also correct. But what's the potential problem? Anyone can think about that? There's nothing wrong.
Can you repeat the question?
Oh, repeat the question. I say that you start with a large denomination, right? Like a 25 cents, try first, then 10 cents or whatever. He said that you try the small one first. If it doesn't work, then you try the larger one. It's a reverse.
The small one's always going to work, though. You're just going to end up with like a maximum amount of the small one. So like if you started with the penny and you're trying to get to 72 cents, you would end up with 72 pennies.
Yeah. But you also raised another interesting question. Is that suppose the 1 penny, right? 1 penny has a limitation. For example, you have 5 1 penny, 10 quarter, 6 nickels, right? But it's not difficult, but you can still do it.
But that's a change of the problem itself, right?
No, it does not change the problem. It's still the same.
Because earlier in the ranking, when you had explained, you said we had unlimited coins.
Yeah, but it doesn't really matter. Think about this. If I give you a test, it says that each denomination has some kind of limit, like a certain number. So what's the difficulty? When you run out of
going forwards from large denomination to smallest denomination minimizes the amount of coins. Going backwards from smallest denomination to largest maximizes.
Yeah. So that's one of the drawbacks. Usually you want to minimize the number of the coins returned, right? Other than that, it's the same. But going back to the other student question, so that I change the problem, actually it's not really change the problem, is that a certain number of coins has some limitation of number of availability. That's fine. When you run out of availability, you have to try the smaller denomination, right? For example, I give you 3 quarter. You try all this, you start with 1 quarter, then 2 quarter, then 3 quarter. Technically, you can try 1 more, suppose, but you run out of quarter. Then what you try to do? You try the dime, right? When you run out of dime, then you try the nickel. So it's the same. All you need to do, just remember, you add in the stack, you add another number there. Number is the number of quarter you try, number of dime you try, to see if that number reach the maximum or reach the minimum, whatever. Does that make sense now?
Yeah.
So it's interesting. If you think carefully, it's not too difficult problem. Okay, so now let's move to chapter 5. Today, chapter 5, another important one. You learned something, but I want to teach you more about chapter 5. It's a divide and conquer. And you probably learn all this divide and conquer, especially in the sorting algorithm, right? Like a merge sort. By the way, can you see it, or it's not shared yet?
Not shared.
Not sure.
Oh, not shared. So I'm still not very familiar with this, how to switch to share mode quickly. Is it shared now?
Yeah.
Yeah,
Yes.
you can share, right? Okay, so this is divide and conquer. So I'll probably go through quickly. You know divide and conquer. Divide and conquer, like you sort this. We don't have to start with sorting. It's just like if you have a big problem, a large problem, what you try to do is divide into several parts. You solve each pass recursively. Then combine solution to each sub-problem into an overall solution. Right? So that's the basic idea. Typically, we use to divide 2. Then you think about this later. You once you learn, probably you can answer already. Right? So why not to divide into 3 or 4 instead of 2? Anyone can give me answer? Why typically people just divide into 2, not 4? No answer? Actually, I ask an easier question. Easier question means that 2 and 4, what's the relationship 2 and 4? You
Maybe we can divide twice and.
Yes. So that's very easy, right? So that means that you divide twice, but then make it the problem or explanation or whatever coding simpler, because you only deal with 2 parts, right? So 4 parts, you have to write 4 parts. Basically, it's a repeat of the 2 parts twice. And how about 3? Just give you an example. Is a 3, obviously the depth of the tree is like a partition, right, to many pieces. The depth will be smaller. It's not a log base 2, it's a log base 3. But you do some simple mathematics in terms of amount of work is still similar. Means that the asymptotic complexity will not change, right? Unless extreme situation. So that's why most people, we deal with the 2, which is easy, half. Although when you run into situation is that, let me just give you an example. You tried 2, right? Always keep on divide 2. You usually assume that the original number is 2 to the power of k. For example, 16, you divide to a, and 4, and 2, and 1, right? It's easiest. But in reality, it's not. But that can be easily bounded. For example, 12, right? 12, you divide into 6, then to 3. Then how you deal with the 3? Then divide into 2 and 1. So one simple argument is that you divide the 12, right? It's between what? Between 16 and 8, right? And if you can prove that the complexity between 8 and 16 are the same, so it doesn't really matter, right? So that's why you sometimes don't deal with those trivial things. And in lots of cases, just assume that the n, original n, is to the power of 2 to the k. Then you can equally divide, right? Don't deal with those. Okay. And usually, if you do this divide and conquer, the complexity will be better, assuming that the amount of work after each level, we call this level divide, is n. And for a size of n, you only need a depth of log n to reach a trivial case, like only 1 unit. And if you use a brute force or what kind of naive way, usually it's n squared. And I already assigned homework number 2, so lots of problems like this. So you have to be careful, use a divide and conquer, you get a better complexity. So that means you run faster. So let's look at some example. I don't know why this does not move anymore. Okay, merge sort. So we're not going to discuss different sort. This is just sorting applications. Right? There are lots of many application sorting. Especially now you deal with data. We're talking about big data, and you want to sort. But still be careful. When you try to solve a problem, you don't have to sort all the data. For example, if application said find the best student and the worst student in terms of GPA, do you have to sort the whole list? Probably not. Why is that? The reason is that You sort the whole list, it costs n log n, right? So n log n. But finding the best student, you only need n comparison, right? You keep a variable, just keep the best. So whoever the best one, you just store there. So it takes n. And if you want to find the worst student, you just run it again, and you get a worse student. So it's 2n. So it's much better than sorting. But under some situation, the boundary is not that clear. Right? So this one probably you need the knowledge. Hope you learned this in the data structure class. For example, suppose in this class, we have n students. And professor want to identify the top k student. Top k student. But I'm not saying that top k, what's the k value? If k is a 1, obviously you don't need to sort. But if k is n or close to n, say half of n. So I just say I want to find 50% of the students, top 50 students. So what are you going to do, right? But what happens if something even in between, for example, 100 students, I say want 10 students, or some number, or square root of n, log n. I say top log n student, top square root of n students, top. What data structure you will use? Or you decide to say, do I need to sort or not to sort? Anyone can answer? Don't be afraid, just we have some interesting discussion, right? But I guess that you all understand the problem. You find one top student, you don't need to sort. If you find you want to rank all the students, you have to sort. But what happens if it's in between? Something that the top k, where k is a function of n, like the square root of n, log n, what kind of data structure you will use, or what kind of algorithm you should use. Definitely not a sort. Or are there any adaptive type of?
Maybe max heap or?
Yeah, that's very good. That's, you really learn this heap. Heap actually is in some kind of a middle. Right? You probably know that how much it costs to build a heap, right? Which is a kind of linear. But when you find one max heap and you have to update heap, it costs log n. So that's actually it's an interesting balance between that. Right? It's not really sorted. Heap is not a really sorted sequence, but there is some kind of order. The top one is the first one, right? So I'm not going to go through this detail, but you can see that in order to fully understand those different data structure, so you need to look at the application. I already showed you example of stack. Now the heap application can use something that not really sorted. Sorting is the optimal solution. Heap is actually the good solution. Okay, so let's continue. All right, so this sort, which is very easy. So this algorithm accredited to Van Neumann, right? We all know that John Van Neumann is like a founding father. So basically in computer field, there is, I would say, 3 most important person. We already discussed one in terms of algorithm, Dijkstra. And this one, Van Neumann, is the computer architecture, right? So he proposed architecture, like have a CPU, like central processing unit. There is some storage and register. So computer architecture is like a finding one. Very important, computer engineering. Another important one is a church, right? Or means that or Turing, sorry, Turing machine. Turing machine is like a very theoretical, it means computability. So anyway, so when Neumann proposed this divide and conquer for solving the sorting problem. So the idea is simple, is that suppose I give you a sequence, you want to sort the sequence A, B, C, D. So you divide the sequence into half. So how much time you divide? It's easy, you just point to the middle. So we use notation of O1, means that constant time. You see, divide constant time. Then you sort, but you don't know the complexity. So then you learn this mathematics or discrete math. So suppose the complexity is T, solving a size of N, but you're solving two sorting subsequence of size N divided by 2. So that's why it's 2 times Tn divided by 2, right? That's one. And the other one is a merge. Merge, or I think we already discussed. How you merge two sorted subsequence. All you need to do is just add a pointer to the beginning of these two sequence, right? You just move each comparison, you move the pointer to the right one position. Sooner or later, you just do it all, right? So it will not take more than n shift. So that's the merge process. So it takes n. Then we can do it recursive expression. So here we use some kind of simple mathematics. Oh, this stop again. Right. So let's just see how you do the merge. Merge is easy. How you do this is a linear number of comparison. So this notation means a subsequence left and subsequent right. And you see this shaded area. This means that it's already compared. So you have a pointer. Now you point to the O, another pointer point to the N. So this one you already sorted. You compare this one. A first, you put the first one. Then the G, then you put the G. Then H, you put here. Then I is here, right? And so on. Which is a mistake. There should be L here. There's L missing. But now you compare O and M, and whichever smaller, M is smaller, you put the M copy here. Then you shift the position to the next one, right? So you can see the pointer is always move from left to right, either on the left substring or right substring. Sooner or later, one of them will be exhausted, then the other one just copy. Okay. So I remember a while ago, I would say like 30, 40 years ago when we learned data structure, people focus on the so-called in-place merge. In-place, what mean in-place? In-place means that you don't use any extra storage unit because at that time storage is kind of expensive. Right now it's so cheap, right? You buy a disk. So what means the in-place? It really means that the algorithm I described, you have to introduce another copy in terms of storage, right? So you have to introduce another array to put that. So there is some kind of in-place merge means that you don't introduce any, or introduce a constant number of extra position or memory to hold the result. So that means you have to reuse those space. But right now, no one cares too much, right? Because now the storage is not a big deal. Right? But this one credit to the person who invented this in-place merge means that using only a constant amount of extra space or without extra space. Okay. Now let's do some mathematics. So, and this is actually a very good example to show you that sometimes you don't want to go to the extreme case. I mean, you start with a simple one. So we know that we divide this into 2. So many students will worry about this one, right? If you're really meticulous, say, if you divide a string of odd number, you cannot really divide into exact 2. So that's why you have one is a ceiling, the other one is floor, right? 0 and 4. But this looks very messy. You see that? This, for example, is an odd number of 9. So one will get 5, the other get 4. So that's why you have this notation. But if I give you a perfect number, it means like 16, you don't need to worry. You only need to worry about n divided by 2, right? So that's why one approach is that you just simply use this n is 2 to the power n, k. That makes it easy. So if we solve this problem, you'll become n log n. So how you do that? Right, how you do that? Let's just look at the 3 methods. And you need to know this one. I assume that all of you already know because this one is covering the data structure, especially the algorithm program technique. Right? But here just give you a little detailed one. So we can start with a simple one. Actually, this is the best strategy. It's like you just expand. And we use this example, you sort both half, and we don't worry about even odd, right? So assume everything even. And you don't even need to worry about whether it's a 12 or 16. So we assume it's always 2 to the k, so you can always be perfect divide. So the idea is this one. So initially you have n. You see this tree looks very nice tree. So you have n, then you divide the half, right? N divided by 2. I have 2 copies of 2. Then you have 4 copies of n divided by 4. So you can see that in terms of the cost, so that's very important, the cost. Cost means the cost of merging. What's the basic cost? Its cost is just merge, right? And you merge. These are all the costs. And you can see that the cost for merging the 2 is n. The cost for this one is this. And if you add all this together, if you do some simple mathematics, all this is n. So that means the cost of all this is just n. So you don't even need to do any sort. I mean, the sort to become a sequence of merging process. Start with, you can, if you think about this like a bottom up, right? You have a 2 element, you don't need to sort. You just merge. You merge become 4 elements. It's assorted. Then you sort these 2 4 elements, whatever, divide by 4, then you get a larger one, all the way to the end. So all you need to do is just calculate the total cost for the merging. So that's the cost it turned out on each level is exactly n. And what's the depth of the tree? And we know that this is a perfect 2 to the k, right? K, so which is log n. When you should stop, when you have only 1 element, you should stop, 2 element, whatever. So that's why the cost is log n, which is depth, times the cost at each level, which is equal. Otherwise, you just summarize all this. So it's n log n. Right? Is that simple? So this is how you solve this recursion function. For 1, if you have 1 element, the cost is 0 because you don't need to do any merge. You start merging for 2 elements. Right? So that's a cost. All right, this is the first solution. The second solution, it's just another way to do this kind of argument. Although they also give a special name called proof by telescoping. So basically do some kind of manipulation on the left-hand side, right-hand side. Both sides divide by n. See, this one divided by n. So it's Tn divided by n, right? This one divided by n is 1. But if you move this 2 down there, then it becomes what? T size of n minus 2, n minus 2. You see that? Then you can see that this left-hand side, the right-hand side, this one is just a special case. Each time you divide by the size of n by 2, right? So you can imagine this new functions of Tn divided by n. You convert this one and you change this one divided by 2, you add 1. Then you keep on dividing another 2, you add 1. So you notice that every time you add 1, is divided by 2, you add 1 element. So this is how you calculate. And you get that Tn divided by n equals log n. Immediately you see that Tn equals n log n. So this is just a simple mathematical, but more interesting one, which is very general. Assuming that you already know the result, you want to validate your result. Obviously, if you don't know the result, you have to use the approach we just discussed. If you don't know the result, what you can try to do is prove by induction. And we assume that you all know the induction process. For example, basic case for 1. Why this is a trivial, simple case? Because for 1 element, you don't need a merge. So the cost is 0. It's correct. Then your induction assumption, suppose this is true for n, or usually say k. Then you want to show that this increase by, you double, so 2n, it work. Show that 2n equals that. So what you can do is that you just replace n by 2n. You see the equation, 2n, and there's 2 to tn, right? That's the same. You just copy this one. But this tn, you use induction hypothesis, right? Tn equals n log n. You put in that. But you know that simple logarithmic property means that n, if you multiply inside 2, is equivalent to -1. That's very simple. Because this is equivalent to like a minus log base 2 log 2. So it's 1. Then you do some simple manipulation and you get the 2n log 2n. So you prove that. That's the proof by induction. Remember, these 2 strategies different. One is that if you already know the result, you just want to validate. Obviously, you can use this induction. Otherwise, you have 2 solutions. You either guess a solution, then you try to prove by induction. If your induction method is correct and your guess is correct, you should be able to prove by induction. Or you say, how can I guess? The best way is using this tree structure, right? You partition the problem 1 by 1. Then on the right-hand side, you calculate the merge cost. Combine, not necessarily merge. Anything like 2 subproblems, how you combine. What's the cost of combining? In this case, it's relatively easy because sorting is relatively easy, but in some cases it's not. We'll see an example after the break. Right? The merge sometime or combine is not that simple. Then once you get the cost of at each level means that you have lots of copy, right? Then you find the cost of combining at each copy, then you multiply the number. So that's why you get this 4 times n divided by 4. It turns out to be all n, uniform. So it's n log n, okay? And if still not certain, I say, oh, I want to validate, then you can use the induction process. Right? So you can use a multiple way to validate each other. Okay, so this is the method. I just want to briefly mention about what happens if you're really picky. Picky means that are you really worried that my assumption is too strong? Strong means that I start with n with a power of 2 to k, right? In real world, it's not that perfect. First of all, even you have an even number, it may not be even number is 2 to k. Or you may situation that you come with start with an odd number, then you have to use this 0 and 4 notation. Right? But even for this one, it's not too difficult, just a little messy, Okay. So again, you start with you have to really guess me. So that means this one is no more than n ceiling log n. You can do the induction process. Again, use n1 for floor, n2 for seal. Then you can just replace this n1, n2. One is ceiling, the other one floor. You replace by ceiling and floor. Right? This is the induction hypothesis. You replace that. And this one is no more than because N1 is a floor, seal is larger, no more than at least the same size, right? So you replace N1 by N2. N2, remember, is ceiling. It's at least as large as the floor. So now once you get the both sides N2, then you just combine. Then combine N1 plus N2 is N, right? That's how we divide this N into one seal, half ceiling, half floor. Then you get this number. Then you do some simple manipulation. This one need to convert back to N. So on the right-hand side, there's some kind of seal flow calculation. I'm not going to go through that. It's not too difficult, but it's just a little annoying kind of detail you have to pay attention to. Eventually, you prove that this one is still less equal to N log N. Okay, see. But you can see this is much messier than the previous one because you don't have that assumption of 2 to the power of k. But you can still manage it. So then there's a 2 exercise. I'm not going to go through this one, but you can just using you can do some exercise. The exercise that this is a good exercise, like using recursion tree to have guess a result, then apply the induction to prove, right? Like this one, then this one is slightly different. You divide into like a 3 copy, right? 3 copy. Then this is the cost of this, right? Like a combining. And this is one like a case of different size. Right? And this is a good example. Also show that, in fact, this is a good example in the sense that to show when you divide into 2, even it's not a perfect divide, not perfect half and half. Obviously, you say half is always better. As long as that they don't differ by a constant ratio. You see that one is 1/3, the other one 2/3. 1/3 and 2/3. But the complexity turn out to be the same. Equivalent to like half and half. Why is that? You can draw a tree and it looks like basically the depth of the tree will be a little bit longer, but asymptotically it does not really change. It's just like a log base, slightly different, right? For the log base 2 versus log base 1.5. This actually is an example log base 1.5. Right? They differ by constant, not really matter. That's why it's important in the complexity theory. People do not worry about some of the constant, right? Constant multiplication or addition. That's why I use a big O means at the most. Notation sometimes uses theta to be exact. And you can even draw a tree. Looks like it's a little bit ugly, but it's fine. I think I need to draw the diagram here just to show you what this really means. I think we already kind of run out of time, but once we had this diagram, so basically you have an n, this dividing to n3, this is 2, right? Like this. Then this is further divide, this is 9, and this is a 6. Oh. This it's just continued. This is 1/3 of this. I think I drew it wrong. So this is a 9, and this is a 9, 2, right? And this is a 9, 2. Is it correct? Right. So you can continue, divide. But what's this ultimate tree looks like? The tree shape looks kind of very ugly. It's like this. I mean, this is kind of very long, but it's not particularly too long. What's that? If you go that way, it's always reduced by 1.5. So it's a log 1.5 n, right? But what's the difference between log 2 base 2 n versus log base 1.5 n? It's the same. It's just by constant. But the shape of tree is kind of unbalanced, right? So that's why in terms of asymptotic complexity, there's no difference. Okay, let's take a break. We'll start after in 10 minutes.